In this lesson, we're going to start looking at optimization problems or optimizing problems. And today we're going to look at creating the model. We started yesterday with 6.3 and looking at how to model linear inequalities. This is pretty much the same thing. We're going to give some special names and use some terminology, and I'm going to lay out some of the steps. And then our last lesson in this unit, we're going to put it all together. So an optimization problem is a problem where a quantity must be maximized or minimized following a set of guidelines or conditions. We're going to have some constraints. That's our limiting condition of the optimization problem, represented by a linear inequality. So, we'll look at that when we look at the examples, what an example of a constraint would be. If I think of yesterday's questions, the fact that the values needed to be whole numbers is a constraint. The fact that the numbers, well, they are whole, but are also positive numbers, that's a constraint. An objective function is an optimization problem, the equation that represents the relationship between the two variables in the systems of linear inequalities and the quantity to be optimized. And then the last term here, feasible region, the solution region for a system of linear inequalities that is modeling an optimization problem. So that's our stippled or shaded region that we'll have a look at as well. So here's a bit of a recipe that we can find useful when creating or modeling an optimization problem. Step 1, identify the quantity that must be optimized. Look for keywords such maximize, minimize, largest or smallest, greatest or least. Step 2, define the variables that affect the quantity to be optimized. Identify any restrictions on these variables. 3, write a system of linear inequalities to describe all the constraints of the problem. Graph the system. 4, write the objective function to represent the relationship between the variables and the quantity to be optimized. Okay? Now we've got one word saying restrictions and one word saying constraints. Okay? And those are sort of interchangeable. There's specific restrictions that we're talking about. So that's really your whole numbers, your positive values. And then your constraints are the constraints that are set by your linear inequalities. So whether it's greater than or less than, those are your constraints that we'll look at further. Okay, so let's look at an example and it'll make a little bit more sense here. So here's one with whole number variables like we were talking about before. So we've got a toy company that manufactures two types of toy vehicles, racing cars and sport utility vehicles. Because the supply of materials is limited, no more than 40 racing cars and 60 sport utility vehicles can be made each day. However, the company can make 70 or more vehicles in total each day. It costs $8 to make a racing car and $12 to make a sport utility vehicle. There are many possible combinations of racing cars and SUVs that could be made. The company wants to know what combinations will result in the minimum and maximum costs and what those costs will be. So in this example, we're really going to spread this out and go through it step by step. And then in the next example, we'll do the same thing, but more like what you would do for like an assignment or a test or practice question. So here for A, reminder, what are the two variables in this situation? So let's define our variables. I'm going to let X be equal to the number of SUVs and Y be equal to the number of racing cars. B, write a system of 3 linear inequalities to represent these conditions. So first one says the total number of racing cars that can be made. And if we go back up here, no more than 40 racing cars can be made each day. So racing cars is Y. And we've got 40, but if it says no more than, That would mean less than or equal to 40. The next one here, it says the total number of sport utility vehicles that can be made. So it says 60 sport utility vehicles can be made each day. So no more than 60. That would be X is less than or equal to 60. And then the total number of vehicles that can be made. And it says here the company can make 70 or more vehicles in total each day. So adding them up, X plus Y, the total number of vehicles greater than or equal to 70. Okay? C. What do you know about the restrictions on the domain and the range of the variables? I was going to say vehicles. And explain. So we know here, because we're counting vehicles, that X and Y must be whole numbers. And the solution set must be discrete. Graph the system, choose at least 2 points in the solution region that are possible solutions to the system. Okay? So before I graph on the next page, I'm just going to write out our inequalities. Our first one was y less than or equal to 40. The second one, x less than or equal to 60. And my third one, x plus y greater than or equal to 70. And I'm going to solve for y here, greater than or equal to negative x plus 70. How did I get that? I subtracted x from both sides. Okay? So I'm going to graph this at the bottom here. Now we could put 2 of our 3 inequalities into our graphing calculator here. Just going to clear out what I had before. So I can put in that the 40, y is less than or equal to 40, and I could put in that y is greater than or equal to negative x plus 70. Now, hitting zoom 6 I know right away isn't going to work. Why? Well, the y-intercept of that is 70. When you hit zoom 6, that's out of the range. So I'm going to change my window so that it accommodates that, okay? X min and Y min are fine, but let's make my Y max greater than 70. Maybe I want to make it, I don't know, 90 or 80. Change it to 80 if you want. Okay? And I'm going to just do the same for my X max. And then hit trace. And you can see that those 2 lines show up. Now, how do I deal with my vertical line? We'll do that in a minute, okay? Because my vertical line's at x is less than or equal to 60. And we'll see how that fits in. So if I look here, I'm going to find my y-intercept, which I know is going to be 70, but we can do that again in a second. Value. I'm going to put in value of 0 for that. And you can see that it is at 40 for that line, and I go up to 70 like we thought before. So the y-intercept of our first inequality, our third inequality is 70, and for this one it is 40. Let's write that down here. So those are my y-intercepts. Let's go back and find our x-intercepts. Really, there's only the one besides our vertical line. So second trace, 0. I'm on the wrong line, so I'm going to click arrow up so I can hop onto the line I want. Move all the way down there. So that's left bound, enter, right bound, enter, and then enter again, and that happens to be at 70 as well. So put that on. Now, our vertical line that we can't see is at 60, right? But I can go second trace value, put an X value of 60 in, enter, and it shows me that it crosses my horizontal line at 40, and it crosses my diagonal line there at 10. So X is 60, Y is 10. So those two, when I connect those 2 points, I could get my vertical line there as well. So let's draw these lines in, and then we can put those 2 points in and connect them as well. So looking at my inequalities, if I just flip back for a minute, they're all or equal to. So I've got all solid lines there. Don't forget to use a straight edge. So draw that in. Okay, so we have 2 of our 3 inequalities drawn there, and our last one is what we had on our graphing calculator here, and we can see that that crosses at 60 and 40. So if that's 70, then 60 would be very close to that right here. And then on the other one, I should just put that here. We're graphing this at 60. And then that point would be 40. And then on the other one, if I jump down, it's at 10. Okay. Draw my vertical line there. There you go. So labeling these, this is inequality 2, this was inequality 1, and this one was 3. So all I have left to do is to label these important points. So we said this one was at 60, 40. We said this one down here was at 60, 10. And we didn't quite get that one. How do we get that one again? That would be our intersection. So second trace 5, enter, 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 and that's at 30, 40. All that's left is to shade our stipple. And in this case, we know that we're supposed to stipple because it's discrete data. Where am I stippling? Well, I'll just use a highlighter here. It says that if we look back at our inequalities on the previous page, y is greater than 40, x is less than or equal to 60, and y is greater than or equal to negative x plus 70. So I'm shading below, shading below, shading above. So shading below this first one would be here, right? Shading below my vertical line would be the same as shading to the left. So that would be everything here. And then shading above my diagonal line, or inequality 3, would be here. Oops, we already used that color. Okay, so where do we have all 3 colors overlapping? that would be in this triangle region here. And you could see I didn't shade, but I stippled because we've got whole number values. Now, it's not always going to be inside the triangle. Often students do so many examples where the stippling's inside the triangle that they always go straight there. But just be really careful to make sure you test all of those inequalities out to see exactly where they are overlapping. So let's look up here at E. It says what quantity in this situation needs to be maximized and minimized. Minimized and maximized. Write an equation to represent how the two variables relate to this quantity. If you look back to the previous page, the key here was when they said here, the company wants to know what combinations will result in the minimum and maximum costs. So that's what we want to minimize and maximize is the cost. And they give us the information right here. It costs $8 to make a racing car and $12 to make a sport utility vehicle. So we're going to use all of that information here. So cost must be optimized. So cost is equal to 8x plus 12y. Now, what we're going to do with that equation, okay, is we're going to test it out. It says each combination below is a possible solution to the system of linear inequalities. 40 racing cars and 60 SUVs, 40-30, 10-60, and 30-40. So what I want you to do is test this equation out. So we actually got an equal sign there for each one. And you're going to see which values give you the most and which values give you the least. And if you look where those numbers are coming from, 40-60, right, is here. 60-10. 40-30 is here, 60-10 is here, and then the last one is 30-40. Again, but flipped around, okay? So we're getting these corner points are exactly what you're testing out, okay? So let's go ahead and try that out. I'll do the first one, and then I'll give you the rest of them. You guys can try them out on your own. So 8 times 40 plus 12 times 60, that would give me $1,040. So go ahead and try the other combinations, and then I'll put the answers up in a moment. Okay, so once you're done all that, you can make an observation about the values here. What do you notice? Well, this one here, this combination, costs the most. The maximum, right? And this combination here costs the least. So the minimum, that's minimizing. Okay? So you can see by testing different combinations into that equation, you can draw different conclusions about the situation. Okay? Let's try another example. Example 2. Creating a model for optimization problem with whole number variables. Same idea. 3 teams are traveling to a basketball tournament in cars and minivans. Each team has no more than 2 coaches and 14 athletes. Each car can take 4 team members and each minivan can take 6 team members. No more than 4 minivans and 12 cars are available. The school wants to know the combination of cars and minivans that will require the minimum and maximum number of vehicles. Create a model to represent the situation. So, as usual, start with defining our variables. Let's let x equal to the number of minivans and y the number of cars. Our restrictions are that x and y are whole numbers, and the solution set is discrete. Okay? Constraints, those are our inequalities. So our constraints, if we go back up here, we look at them one at a time. We no more than 4 minivans and 12 cars are available. So y is less than or equal to 12. That's for the cars. My next one, x is less than or equal to 4. That's for the minivans. Okay? Back up here, it says each car can take 4 team members, and each minivan can take 6 team members. So that would be 4y plus 6x. But now the question becomes, what's the total number of people that they need to fit into these vehicles? Well, there's 3 teams, if you see up here, 3 teams, and each team has no more than 2 coaches and 14 athletes. Okay, well, 2 coaches and 14 athletes, that gives me 16 people, but I've got 3 teams, so we have 48 people that we need to put in these vehicles. So no more than would be less than or equal to 48. And that wasn't intuitive when you were reading that, right? So you had to get that information from there. Rearrange and solve for y here. Moving the 6x, 4y less than or equal to negative 6x plus 48, and then divide through by 4. So y is less than or equal to, you can change that to negative 3/2 or leave it as 6 over 4, it doesn't matter to me. You can even leave that as 48 over 4, or you can change it to 12 if you want. Okay? Now, what's next? I've got my variables, I got my restrictions, I got my constraints, so now we need to graph this. So I drew myself my axes there. Let's pull out our graphing calculator. Clear everything out. I've got my first inequality is 12. Second is 4, I can't put that one in. And then the third one, negative 6 over 4x plus 48 divided by 4. 48 divided by 4 is 12. So let's change my window. Well, you can add zoom 6 if you want. You can see part of it, right? But you can't see the whole thing. And we know that that's going to be up at 12, even from this equation here where it says y is less than or equal to 12. So let's just change our y max to 15. Sometimes that's the hardest part, is figuring out your window. Hit trace. By doing that, I can see more of what's going on. Okay? So that value, I can see already at the bottom, that's my y-intercept is 12. So I'll put that in here. I'm going to draw that line there. At 12. And don't forget to label that, so that's inequality 1. Okay, and let's go back. We're going to need our x-intercept there. Make sure I'm on y2. Left bound, enter. Right bound, enter, enter again, and that x-intercept's at 8. Okay, so let's draw that. That's probably a little too far over for 8. So let's draw that line in. Remember, using a straight edge, and these are all equal to, so I didn't really worry about a dashed line. They're all going to be a solid line. Now remember, when we have a value with an x in it, we can just go second trace value and put in that x value, and it'll show us those intersecting points. So that's at 412 and 46. So if that's 8, then 4 is about halfway. That vertical line would go up through there and would cross at 412 and 48. Okay, now all that's left is our shading, in this case stippling, because it is discrete, right? Whole numbers, discrete solution set, so we need to stipple. So where would that be? Greater than inequality 1, less than inequality 2, in that case it would be to the left, and then less than inequality 3. And I didn't label those. This would be 2, and this would be 3. So where would we end up? Would be right here. So you could see that it's tempting to go inside the triangle, but in this case, that's not actually true. The stippling is just dots indicating that this is exact values inside whole number values, to be exact. Okay, so last thing we want to do, create a model representing the situation. We didn't quite talk about the optimization function, or the objective function, sorry. Optimizing the problem. So it says the school wants to know the combination of cars and minivans that will require a minimum and maximum number of vehicles. Okay? So to get our objective function, this is going to be an actual equation. We're going to introduce another variable. Let v equal the total number of vehicles. And that would be x plus y is equal to v. Right? Total number of minivans plus the total number of cars. And if we wanted to actually figure out what the maximum or minimum was, then we'd have to substitute some points. And as we move on in future lessons, I'll show you exactly what points you want to test in order to find the maximum or minimum. Okay? There is one more example in our notes, but I'm not going to worry about that. We're going to do lots of examples in class. Thanks for joining me today.